Go ahead and get started. I'm glad to see all of you today. I hope that you're having a wonderful day so far and a happy Halloween. I was trying to figure out what I should do, for my costume. And then I decided that probably the scariest thing I could possibly do was walk into the class with a stack full of midterms to return. That might get everybody a little scared. So I decided to leave it at that for now. I was up until about 2 o'clock in the morning finishing that grading. It was a very, very excruciating grading session. I started it on Tuesday night, and with the first midterm, I was done by lunchtime the next day, but this was a little bit of a different story. So I'm going to tell you about that later. I'm going to pass back the exams at the end of class. Because if I do it right now, everybody's just going to be looking at their exams for the next half hour and not listening to me. So I will wait until the end to return your exams and talk about how that went. But I didn't want to publish, so I didn't publish the scores quite yet on Canvas, but the exams are graded. So you guys will get those back in just a little bit today. Okay, so that's that. We've got nothing else due for this week other than the video that you guys watched. You don't need to take notes on this part, by the way, because I'm going to pass out a handout on that in just a minute. But if you wanted to write anything down at all, it would probably be this picture over here. A little bit of a discussion for you here. But anyway, yeah, it's great to have you all here. There's no other homework for this week. I think your next assignment is going to be due on Tuesday, and it will be about the kernel of a linear transformation. And gosh, we even have a homework assignment for Thursday. And Thursday's assignment next week will be about the range of a linear transformation. So the two main topics of the video that you guys watched will be on that. So I'm going to take just a little bit of time today to review what was in the video that you guys watched. I think almost everybody watched it. If there's anybody here who has not yet submitted their notes or scanned their notes into Canvas, you should do it like ASAP if you want credit for it. It was supposed to be due before class started. But at any rate, I am going to review the video briefly and kind of tell you some new things today as well. So remember that the setup of this is we have this linear transformation T, right? And it goes from one vector space V to another vector space W, right? And so we can think of it as a set of arrows going from the left to the right. Inputs from V, outputs in W, right? Okay, and then in the videos that you guys watched in these last couple of days, I talked about the so-called kernel and range of this linear transformation, okay? The kernel and the range. So I put the kernel part over here in red. The kernel is sort of sitting inside of V. It's sitting inside of the input vector space, whatever V happens to be. And what is it here? So I put it in red. The kernel of T, that is those vectors in V that my linear transformation sends to 0. In other words, it maps them under the function to 0. So in terms of the picture, right, you can kind of see if I have a little part of my vector space V where I have some vectors that are getting sent over here to the 0 vector of W, then that set of vectors is the kernel. Okay, so I kind of shaded it in here, right, in the red highlighting. The red section of V, that is the kernel. And so it's the set of vectors that get transformed to 0, okay? And I said it in the video, but I did not show it, that the kernel of T always forms a subspace of V. So what I would actually like to do first today, guys, is actually put down that proof. So before I go any further, I'm going to prove, let's put a little asterisk in the notes here next to that little observation. The subspace of V, kernel of T is a subspace of V. I'm going to put a little star here in the notes. And then what I'm going to do is come over here in this little white space, and I'm going to try to do the proof of the star. Okay, so I'm going to prove that the kernel of T is a subspace of E. Actually, that was a problem in the review packet for the midterm. I had 3 people come up and ask me, oh, do we have to know about the kernel for the exam? And I said, well, it wouldn't be that bad to be thinking about it, because showing that something is a subspace was definitely something you were supposed to be ready to do on our exam. And it involves 2 parts, right? We all know this, to show that something is a subspace. What is it? We have to show that, can somebody remind me, what do we have to show that something is a subspace? Liam? Exactly. I have to show closure under addition and closure under scalar multiplication. So let's take those one at a time. To show the closure under addition, we have to start with 2 vectors in the kernel of T in this case, and then add them together. So let's let V1 comma V2 be elements of the kernel of T. So I would start off with that. And this just means that, what that means is that thus, if we apply T of V1, we're supposed to get 0. That's what the kernel of T means. And also T of V2 should also be 0. So both V1 and V2, those are 2 of the dots that are in the red part of the shaded red part of my diagram here. Okay, so we start with that. And now what I would like to do, and stop me if there's any questions here though, by the way, guys. What I would like to do is look at V1 plus V2. And I need to check, is that still in the kernel? Well, the way I check if something is in the kernel is I transform it under T, and I ask myself if it still equals to 0. Let's give that a try. Okay, so then I'm going to do T of V1 plus V2. Again, why am I going to do that? Well, it's because I want to look at V1 plus V2. I want to know, is V1 plus V2 in the kernel of T? So what, when you see something like this, what is your, I mean, we want it to be equal to 0, but I can't just write 0 yet. I have to derive that that's correct. What is your knee-jerk reaction, sort of your immediate thought when you see T of V1 plus V2? Remember, T is linear. Evan?
Be able to split it.
I should be able to split this up into T of V1 plus T of V2. That's because T respects addition, right? That's part of what being linear means. So I can write this one, guys, as T of V1 plus T of V2. That is because T respects addition. Okay, and then what is T of V1? We just wrote it down a minute ago. That's just the 0 vector of W. And T of V2 is also just the 0 vector of W. And of course, 0 plus 0 is 0. Okay, great. So that's what we were hoping would happen. V1 plus V2 is in the kernel of T. Let's just write that down. So V1 plus V2 is an element of the kernel of T. Okay, great. That's the first part. Now I also have to show the closure of the scalar multiplication. Let me just mute my handout for just a second. I'll write it over here. The closure under the scalar multiplication part, this would look like a pretty standard write-up as well. I have to just take one vector from the kernel and scalar multiply it by k, right? So you guys remember how this might look. Let k be an element of the real numbers. And then let's just say V1 as above. So we'll take one vector and then one scalar. I usually use k for my scalar and the vector V1 as above. And then I want to look at the scalar multiplication of k times V1, and we're going to plug it into T. So I'm going to calculate T of k times V1. What's the first thing you're thinking about doing right here? Take the k out. Exactly. I can pull the k out in front. So this becomes k times T of V1. And we still know that T of V1, since V1 is as above, we had already written down that that's just the zero vector. And we're multiplying it by K now. And of course, that's just going to give me the zero vector back again. Awesome. So that's what we were hoping would happen. And so we can conclude now that K times V1 is in the kernel of T as well. So we put a check there. I should have put a check mark over here as well for checking the closures under addition and scalar multiplication. Okay. Looks pretty good to me if you guys think that looks okay. The kernel of T is a subspace of V. Of course, you know where we're going to go with that. As soon as we have a subspace, we're going to be asking to find a basis for it, the dimension of it, and so on, which is what you saw those examples in the video that the videos that you guys watched. So we'll have plenty of chances to practice that. Before I get to those examples, though, I just also wanted to remind you about the range of T. Unless is there any questions so far? Yeah, so this is a great example, or this stuff in red that we just wrote down is a nice review of subspaces together with this new concept of the kernel of T. It's kind of a nice thing to put together. We also have another subspace that's always kind of, part and parcel of the same conversation. We always talk about the kernel and the range together because they are related ideas. The range of T, which is the blue part of my picture here, as I explained in my video, it is just the span of the transformation, the list of transformed vectors from any basis for V. Okay, so you start with any basis for V. I usually would pick the easiest basis that I can think of. It might be a standard basis of just standard vectors in Rn or Pn of R or whatever the vector space is. But pick some nice vectors here that you're just going to transform all of them. And you're going to form the span of those. So if you do that, I say here in blue that this was going to be a subspace of W. Can somebody tell me why I already know that without having to do a whole big proof again? Dorsa? Because it's a span, and anytime you take the span of anything, as we've said many times, it's automatically always a subspace. Right, so the range of T is going to be a subspace of W, and what is it exactly? It's essentially going to be those vectors in W that actually receive arrows. So these arrows are coming over from V to W, and they're hitting certain points that are inside of W. Those vectors that actually get hit as an output from the transformation, those are the range of T. Okay, so it might not be the entire W. W is the big universe that the entire outputs live within, but the actual outputs that are obtained might only be some of the universe of W. So that's why I'm drawing the blue circle here inside of W. But it is definitely a subspace, and so we can definitely, once again, ask for a basis and dimension of it. Now, be a little careful. I've kind of cautioned you about this before. You might be looking at this saying, oh, well, it's obviously n-dimensional because there's n vectors here in this list. But that would not be a very good reasoning, right? Because remember that this list of vectors here could, in fact, be LD. Even if the original vectors were a basis. So the original vectors, V1 through Vn, they are definitely Li because, in fact, they are a basis. But you know what? This linear transformation could create dependencies in the vectors after you transform them, right? That's a risk. That's always a possible outcome of your process. So be careful here, guys, when you're looking at this list of vectors. They might not remain Li after the fact, which means that your dimension for the range of T, your basis, might actually become smaller. And you might have to be a little bit careful about that. So at any rate, does that make sense? This is just a quick overview of the whole thing about kernel and range. let me pull down this video recap. Now, guys, I was trying to prepare for today's class and I was gonna come in here and write all of this back on the board again. And then I realized that that was going to take forever. So I chose not to do that, and instead I made a handout. And I have put this handout in the Canvas website under the special handouts section, but I'm going to pass out a copy of this to all of you, a physical copy of it right now. And so you don't have to take any notes on this. You can just kind of follow along, watch along here. Let me just see if I can have you guys take one and pass those back. Actually, this is probably my original, sorry. Take one of those and pass it back. And then I'll make sure everybody's got one. And then we're just gonna talk through this real quick. Just take a few of those and pass those back. 5, 6, 7, 8, 10, something like that. Just grab one and pass it back. Take one at the two-sided. This is a two-sided handout here. I probably am gonna come up short over there. Did everybody get one back? That's okay. Okay, so guys, what I'm gonna do here. What I'm gonna do here, guys, is quickly review this handout, because this is what you have already kind of watched a little bit on your video that you took notes on. And it's just for example, and actually, okay, when we get to these warm-ups, we might change the numbering of those examples a little bit. So the first example, and this was in the video, is we took a transformation from R3 to M2 of R. Again, you don't need to take notes, just kind of follow along. I'm gonna just kind of quickly review what these examples are all about. So the first example we take as an input, ABC, right? That's a vector in R3, and we're going to output a 2x2 matrix, which is the one I put right here, which has zeros on the main diagonal, and then A minus B plus C, and it's negative on the off diagonal. It's actually a skew symmetric matrix. Anyway, so I've got two columns here where I kind of wrote down what is the kernel, what is the range. And to find the kernel of a linear transformation, you always do the same process, which is you just take your T of whatever your vector looks like and set it equal to the zero vector of W. Now, in this case, my W is 2x2 matrices. So my zero vector is going to look like a 2x2 matrix of all zeros. And so I just simply write that down. Now, when I do that, of course, what I'm really doing is I'm setting this output, which is this 2x2 matrix, equal to this 2x2 matrix. And when you match up the corners of the matrix, it really just reduces to one equation, which is right here. A minus B plus C should equal 0, right? It's a simple little equation. We all can solve that, right? Basically, B and C are free variables, and then we can solve for A in terms of those two free variables. Ultimately, we write down what A, B, and C are into 3 slots here, right? The A slot, the B slot, and the C slot. And then if we want to get a basis for the kernel, we just bust out those variables now, right? So you bust out the R, that gives you the vector 1, 1, 0, and you bust out the T, and it gives you the vector -1, 0, and 1. That's the kernel of T. That's how you calculate it for that particular example. Does that make sense to anybody? Does anybody have any questions on that? I'm going through this fairly quickly, but I will definitely take questions too. So far, so good. All right. The range of T. Okay, so the range of T is the span of a list of outputs of the transformation. Notice what basis I chose. I chose the standard basis of R3, just because it's the easiest one that I know. You don't have to choose that basis. You can take any basis for R3, but the nicest basis is definitely 1, 0, 0, 0, 1, 0, and 0, 0, 1. And I'm just going to transform each of those one by one by one, right? And to do that, I just have to sort of go back to my formula, which is up at the top here. And I just have to put in a 1 either for A or for B or for C into the different corners of the matrix, and then write down the result. So for example, when A is equal to 1, and I put it into that matrix in the top right corner of this screen, I'll just get the matrix 0, 1, -1, 0, like so. It is a 2 by 2 matrix. Right. When I put in B equals 1 instead, I get this matrix right here. And when I put in C equals 1 instead, I get this matrix right here. And what you quickly observe about the three matrices, this is the point I was making earlier, they're no longer Li. In fact, you can see that the second and third matrices are really just the same as the first one, or the negative of the first one. And so you see, I said to remove those. If I want to get a basis, I don't want to have those linear dependencies in there. I don't want to have the same vectors multiple times. So I get rid of them, and I just write down the one basis vector that survives. There's only one, so the range is only one dimensional here in this case. Maybe it's not this obvious all the time. Maybe you have three matrices and you don't even see any connection between them. Well, you can test them for Li because you guys know how to do that now, right? Just lay the vectors into the columns of a bigger matrix. You might have to do some EROs in that scenario, but after you've done those EROs, it is as long as you have any unpivoted columns, as we've learned many times, right? Those unpivoted columns correspond to vectors that you would remove. So if you're wondering, well, how do I know what to remove here from this list? That goes back to the process of shrinking down a set of vectors so that they become Li. Yeah. Everybody with me?
Yeah.
Okay, great. So this is an example where I have a, what is it? A two-dimensional kernel and a one-dimensional range. In my video that you watched, I didn't talk a lot about the dimensions of these vector spaces. Oh, but boy, today am I ever going to talk about that a lot. It's going to be a big deal. So let's kind of start thinking about these examples in that way. A two-dimensional kernel, a one-dimensional range on this first one. Yeah, Yordi, do you have a question?
Yeah,
Yeah, please.
why did you use A minus B plus?
Yeah, this other one is actually just the negative of this one. So technically, I should have written it down on a second line, but it has no new information in it. It's just literally the negative of the first equation, so I only wrote down the first one. You know, again, this handout is supposed to be, I'm just kind of abbreviating the high points. I didn't really show absolutely everything that you could do. Yeah, that's a good point. Any other questions so far? This second example is slightly more complicated, partially because the inputs now look like polynomials this time. E2 of R. So that means I'm going to plug in a quadratic polynomial, and I'm going to spit out, again, a 2 by 2 matrix. This time, the 2 by 2 matrix that I'm going to spit out is a little bit more random in terms of what the entries look like on the right-hand side there. But the process that we carry out here, guys, is exactly the same. We're just going to set the transformation equal to the zero vector. Every time you're finding a kernel of anything, that's always how you do it. Set the transformation equal to the zero vector, and then let the chips fall where they may. Basically, that zero vector has to agree with what this output is. And so every single corner of the matrix over here would have to be 0. And so I've written those 4 corner equations down right here, yeah? And now this time, see, you really probably have to do some EROs, okay? It may not be quite as obvious exactly how to solve this one. So you would just put this linear system of equations into a matrix like we've been doing for almost 2 months now. This goes way back to the beginning of the linear algebra part of the course. So you would put them into this matrix, bring them into row echelon form, and you can see again, I do have a free variable, which is the C variable here, the third column. And so I introduce T as my free variable, and by back substitution, which I will not really go through all the details of at the moment, but you can see what A and B would be equal to. The key thing here, though, is, so let me just jot something down. So if I write down A, B, and C like this is what I saw a lot of on the midterm on Tuesday, which was people putting things in slots. slots are great if we're working in Rn, right? If the vector space, if the universe that we're working in is Rn, then sure, this would be a good way to represent it. But we have to understand where the kernel vectors live. They live in P2 of R, right? This is the quadratic polynomials vector space. So instead of writing 3 slots down like this, we should be representing it as a quadratic polynomial, 1/2 t x squared minus tx plus t. We write it as a polynomial. And then we can still bust out the variables. In this case, I bust out the t. And after I bust out the t, I get my basis vector here. So it's the same process, it's just not with slots, which is very tempting to do, I admit. Questions on that? So we have a one-dimensional kernel here. The range of t, all right, I take the span of the transformation of any basis for P2 of R. I would recommend the standard basis. The easiest basis is just the different powers of x. T of x squared, t of x, and t of 1. Those would be the easiest inputs to plug into t. And essentially, if you're doing that, if you're plugging in t of x squared, then you're really letting a be equal to 1. You're letting b and c both be equal to 0. And if you do that, if you put 1 in for a and 0 for b and c, you get, you get this matrix right here, -2, 0, and then the bottom row is 0 and 6. So just kind of look at this matrix, and wherever you see an a, those coefficients are what you're putting in the corners of this first matrix right here. Okay, and then if I want to evaluate t of x, well, same thing except using b. So everywhere I see a b in this matrix, that coincides to the coefficients that I'm going to write down into this matrix, and I do the same thing for the third one. This time, it's probably not clear whether those 3 matrices are Li or not. And so if I want to find a basis, it's possible I have to remove something. And if I do lay those vectors into the columns of a larger matrix and do my EROs, sure enough, I didn't write it all out on here, but you will find that third vector is coinciding with a free variable. And so we have to remove it. This is the same idea we've been talking about for a while now. We remove that vector and our basis is just the remaining vectors. That's my basis for my range. So far, okay? Yeah, so that was the second example. The third one is even a step harder than the first 2. The reason I say that this third one is harder is that now I'm going to work with polynomials on both sides, inputs and outputs. And the other thing that makes it hard is you'll notice that the transformation is written fairly abstractly here. I didn't write down what t of ax cubed plus bx squared plus cx plus d is. Instead, I just wrote it as p of x. Very, very generic notation. And then the formula is just, okay, we're going to take some derivatives over here. P double prime of x minus 3 times p prime of x. So actually, before you can start doing the kernel and the range, you need to get the more explicit expression for the transformation, right? So in this case, I said, let's first rewrite it as t of a cubic polynomial. So I'm actually going to write it out, ax cubed plus bx squared plus cx plus d. So I took 2 derivatives of it, minus 3 times 1 derivative of it, simplified it down so that it was literally looking like a quadratic output here. And I'm going to set that equal to 0. When I'm setting this equal to 0, remember that's not the number 0. That is the polynomial 0, meaning that it is like, you can think of this as 0x squared plus 0x plus 0. And so all of the coefficients here, right, all 3 of these coefficients would have to be 0. And that's how you get this system of equations again. Okay, so it's kind of similar to the earlier examples. We get a system of equations. This time I can just look at it. A has to be 0 from the first equation. And then from that, I can find out that B is also 0. And from that, I can find out that C is also 0. But don't forget, there actually is a constant term, which is D, that doesn't even show up in any of these equations. And so D is actually free, as you may recall from that video. And so my kernel of T just consists of the set of T. the set of constants. These are constant polynomials, and it does make sense that if I take a couple of derivatives of a constant and subtract 3 times the derivative of a constant, that I would get 0, because we all know that the derivative of a constant is just 0. Right, so this is not surprising that any constant is in the kernel of t. Once I bust out my free variable, I'm left with a basis. Just has 1 in it. So all scalar multiples of 1, which is just all constants, that's what makes up the kernel of t in this example. And then the range, again, I won't drag you out through all this again, but you're just going to take a standard basis, maybe x cubed, x squared, x and 1, transform everything using the new formula that I derived, and I put down the 4 results here. You can obviously see that 0 should be removed. You never want to pay $1,000 to put the 0 vector into a basis. So you'd want to remove that one. It turns out that's the only one that you need to remove. So you can keep the other 3 basis vectors there, and that is your basis. Okay, so that's a nice example as well. Finally, on this handout, I've got this example 4 here, where, this is the very generic one about matrix transformations, and I went through this in the video in pretty good detail as well. If we have a transformation from Rn to Rm, you guys will remember, I hope, that those transformations are always created through the use of a matrix, a fixed M by N matrix. So T of X equals AX. And so if I'm looking for the kernel of such a transformation, I'm just setting AX equal to 0. And that should be something that sounds very familiar, right? That's literally just asking for the null space of A. Right, the null space of A. That's the vectors that the matrix A kills, essentially. A times X equals 0. So the null space of A. So the kernel of T on this kind of an example is always just the null space of A, which we all know quite a bit about already from earlier in the semester. So that's the kernel. And then for the range, this is also something very familiar, because if we take the span of the transformation of a standard basis for Rn, you're just going to take each matrix, you're going to take the matrix A and multiply it by each column vector that's a standard column vector. You're just going to pick off the different columns of the matrix. And the span of those columns is the column space of the matrix. So it turns out that the range of T in this case is the column space of A, right? Totally everything should be making sense. The null space, yep, it's a subspace of Rn. The column space, that's a subspace of Rm. You hopefully remember that from when we were looking at null spaces and column spaces earlier. This is all just consistent with that. Okay, so good. Are there any questions on any of those 4 examples? Let's practice a couple more. I'm going to actually ask you if you've written down these warm-up problems, let's just number these instead of 1 and 2. I'm going to number these warm-ups as 5 and 6, because that way we can make a continuing list of examples that we have. So by the end of this, we're going to have 6 examples of this. Let me bring my computer back up here again. So the first one here, number 5, T is going to be a transformation from the 2x2 matrices to the real numbers. And I'm going to input a 2x2 matrix, right? A, B, C, D. And I'm going to output this number right here, A plus 5D. A week or 2 ago, I showed that was actually linear. So it respects addition and it respects scalar multiplication. This is a linear transformation. But today what we want to do is something different. We would like to find the kernel and the range of T. Okay, so I'll start with the kernel. By the way, there's nothing that says you must always start with the kernel. But I'll go ahead and do the kernel first. So let me put that maybe over here on this side. The kernel of T. Okay, so having watched my video now and kind of having it reminded through that handout, we probably have a pretty good idea how to do this. we're just going to take T of, you know, A, B, C, D, and we're going to set that equal to 0. This is how we do the kernel. We always just set the transformation to 0. And in this case, that just means that A plus 5D would have to be 0. So that's just a single, that's actually not that different from the first example that we did on the handout here, where we have sort of just one equation. We had just one equation here that we had to solve, and so the pivoted variable or the leading variable would be A in this case. But of course, I have 3 other variables, which are B, C, and D. Those are all free. Those are all free. And I'm just going to leave them as B, C, and D for the moment. So I'll just solve this for A. And if I do that, I get A equals negative 5D. And so my kernel of T would be the set of matrices. These are 2 by 2 matrices of the form, you know, A, B, C, D, but now I have to put in what A is. A is negative 5D, and then B and C and D, those are both free. Those are all free. Again, I have to draw it as a 2 by 2 matrix. If you start writing it as 4 slots that are just going in a line, that's not really what the vectors should look like. They should look like this form, a 2 by 2 matrix. And then this is such that B, C, and D are real numbers here, right? Then we finish up our set in that way. And if I want to get a basis, right? To get a basis, all I have to do, as we know, is bust out the variables. So I have 3 variables to bust out. I'm going to do this quickly since we've been doing it for quite a few weeks now. When I bust out the B, I'll just get 0, 1, and then 0, 0 on the bottom row. And then when I bust out the C, I'll get 0, 0, and then on the second line, 1, 0. And finally, the busting out the D variable gives me negative 5 and 0, and then 0 and 1. And that would be your basis for the kernel of T in this case. Everybody okay with that? What's the dimension of my kernel here?
3.
It's 3, right? Because I have 1, 2, 3 vectors there. That's it. So it's a 3-dimensional kernel. That's really looking pretty good to me. Awesome. And then we have to also think about the range. The range of T. What's that again? That's just the span of, I'll just come over here and write this down, the span of, and then I'm going to transform a basis for M2 of R. Does anybody want to help me with that? What basis for M2 of R sounds like a nice one to work with? These are the 2 by 2 matrices. What's a nice set of 2 by 2 matrices to be plugging in? Let me hear from somebody else. Marcus?
1, 0, 0, 0, 0, 0, 1, 0, 0.
Exactly, right. So he's got the idea here, right? You just move a 1 into every single slot of the matrix. That's the standard basis for R, for M2 of R. And so we would have 4 of those, right, in total. And we're going to take the span of all of that. So it'd just be the span of all of that. And what I have to do is evaluate. I have to evaluate each of these. Okay. So let's see. T of, so I can go back to, here's my formula, right? This is what I'm going to be looking at. I need to figure out what is T of 1, 0, 0, 0. And I can see that if A is equal to 1, I'll just get 1 out of that. Right? And then the next one is T of 0, 1, 0, 0. This time B is 1. Everything else is 0. So this is going to give me a 0. Right? When I evaluate T of 0, 0, 1, 0, now C is equal to 1. Everything else is equal to 0. So this becomes a 0. And last but not least, when I plug in 1 for D, and I transform 0, 0, 0, 1, I will get 5. I will get 5 like so. So there you have it. those are the different outputs of that transformation on that basis. But as you guys can obviously see, this is not our basis yet. We would never keep the zero vector in any basis. We would always remove a zero vector from our set because that's not something we need to add to any basis. And 5 is just a scalar multiple of 1. And therefore it would be linearly dependent on 1. And so I could also just as well remove that one as well. And so this time we would get a basis that was just 1 alone. Just 1 alone. That would be the basis. What do you think? Does that look pretty good? Question?
Why did we have to remove the 5?
To get a basis, we don't want any linear dependencies,
Right.
and this vector is actually a scalar multiple of this one.
Oh.
As you can see, if I take 5 times the first vector, if I call this V1, 5 times V1 would be equal to this vector, which I could think of as V4.
Yeah, B4.
So I'm going to get rid of V4 to remove that.
Alright.
Any other questions on that? Before I go to number 6, we now have 5 examples between the 4 that are on the handout plus the one we just did right here. I want to stop for a minute and talk about the sizes of these kernels and ranges. This is actually kind of interesting. Notice on this one we just did, we have a pretty big kernel, 3 dimensions here, but then the range was actually pretty small. And so I actually think there might be something to this. Somehow the kernel and the range seem to be almost playing in opposite directions. And it actually is going to turn out to be quite interesting. So I'm going to come back over here, guys, and I'm going to make a little table that you might want to draw a table in your notes for this. I'll show you what I mean. We're going to take all 6 of our examples and put them into this table. Okay, so here is, I'm just going to go back and write down, these are where my examples are. Right? And all I want to write down on these examples is what was V and W, and then what were the dimensions of the kernels and ranges. So like the first example was T. I've got it on this, I put it back on the screen there. T was going from R3 and I was mapping it to M2 of R. So I just want to keep track of that. And then what I'm going to do, guys, over here, I'm going to make a little table. I'm going to make a little table here, and I'm going to write one of these columns. The first column, I'm going to write dimension of kernel of T. And then in the second column, I'm going to write down the dimension of the range of T. Remember, the dimension is kind of measuring the size of that subspace. Right, so taking a look at this example, let's take a look at it together. We've already done it here. What was the dimension of my kernel on this first example? You can look at the handout if you need to, it's just right here. What's that dimension for the kernel? 2, right? 2-dimensional? Okay, and what about the range? What's the dimension of the range? Just 1-dimensional, right? Just 1-dimensional. Good. So let's put 2 here and 1 here. All right. For that first example. Okay. Now the second example, I'm going to scroll this down on the screen for you just a little bit. On the second example here, we have T going from P2 of R and mapping it over to M2 of R, like that, yeah. And let's make sure we can see the whole thing here. What is the dimension of the kernel of T on this second example? Chris, go ahead. Just 1 vector here, right? Yeah, that's just 1 vector right there. And what about the dimension of the range of T? Anybody? David?
2.
2. 1 and 2. Okay, let's write that down. Add that to our table. We have a 1 here. We have a 2 here. Okay, great. We're going to be noticing something. I'm not doing this just for kicks. There's a reason for this, as you're going to see in just a minute. Let's scroll down to the next example, 3. Example 3, let's see, T, this time T is going from P3 of R, and we're mapping it over to P2 of R.
Mm.
Right? And can somebody tell me what's the dimension of the kernel and the range on example 3? Kernel? 1 vector there, right? And how about on the range? 3, right? 1 and 3. Let's put that into our table. 1 and 3. So it just seems like when the kernel is bigger, the range is smaller, and when the kernel is smaller, the range is bigger. I'm wondering if anybody's seeing the pattern yet. If you haven't seen it yet, you're gonna see it now. Because when we go to the 4th example, and I asked you, so this is, what is this? This is T going from Rn to Rm, right? Our matrix transformation. And I asked you, what's the dimension of the kernel here? Does anybody remember what that word was? The name for the dimension of the null space of a matrix? That's called, Matt, do you remember? The nullity of the matrix. That's exactly right. So that's the nullity of A. Right? And what about the dimension of the column space of the matrix? That's the range. Does anybody remember the dimension of the column space? Angela.
Is it rank?
That's the rank of the matrix. Oh, well. I think we've definitely seen a connection between the rank and the nullity before, right? In fact, can somebody remind me what that connection was? The rank nullity theorem, what does it say again? Go ahead, Leo.
Rank plus nullity equals n.
Rank plus nullity equals n, right? The rank plus the nullity equals n. So if we go back now and kind of use that conjecture on the previous examples, does it work? 3 plus 1. Oh, that adds up to the dimension of P3 of R, right? 2 plus 1, that adds up to 3, which is the dimension of P2 of R. And 1 plus 2, well, that adds up to 3, which is the dimension of R3. Guys, this is not an accident. Let's try 5 real quick here. The 5th example is to see if this is still being confirmed. This was the one we just did on the board here in the middle. T going from M2 of R, mapping it over to R. And what did we come up with here for the question?
I was gonna answer it.
Okay, yes, what is the dimension of the
3.
kernel? 3, right? There's 3 basis vectors there.
And the dimension for RNGT is 1.
The range of T has just 1 basis vector in it right
Right.
there. So we put a 1 here. And now does that check out?
It
With the
does.
formula, if we take the rank plus the nullity, 3 plus 1, or 1 plus 3, I should say, we get M2 of R's dimension, which is 4. Okay, so guys, this is actually a theorem that this pattern that we are noticing on all of these examples is actually going to always be true. So I'm going to come back over here and write down this theorem. It is called the general rank nullity theorem. This is a nice observation. So let's just go ahead and add this to the, by the way, save a little bit of room on your table though, because we're going to do number 6 in just a minute. So save like one more line to put that in. But in the meantime, I'm going to go ahead now and write down the general rank nullity theorem. All right. What it just says is that if T, which is a transformation from V to W, so if T going from V to W is linear, right? If T is linear, then here is the equation, and this is definitely one that you will want to memorize. It's not too hard to learn it. The dimension of the kernel of T plus the dimension of the range of T, right? This will always equal the dimension of V. The input vector space V, it will always agree with that. This is called the general rank nullity theorem. And of course, we see the original rank nullity theorem kind of in this fourth line right here. The fourth example shows that the rank plus the nullity adding up to n. Okay? Guys, I cannot overstate the importance of this theorem because you know what? Most of the time, you're going to know what the dimension of V is. You probably will. I mean, I bet everybody knows the dimensions of everything over here on the left side, right? These are very familiar vector spaces. We know the dimension of V in like all of these examples right here. And if we know that number ahead of time, if I know how big V is, then I can play this equation whichever way I want. If I know the dimension of the kernel, it'll tell me the dimension of the range. And if I know the dimension of the range, it'll tell me the dimension of the kernel. I can play that back and forth as much as I want to. Right. So let's do example 6. Oh, I just erased it. That's okay. I'll write it down again.
Oh my.
I didn't mean to erase the question here. Let's do the 6th example and try to use this theorem to help us do it. So this was a T going from R2, and we're mapping this one to P2 of R via, so I'm just rewriting the problem because I accidentally erased it, T of AB, and this was equal to A plus the quantity B minus 2A x squared. And so let's just do one more and then we'll fill in the information. So I guess in my table, I have T going from R2 and mapping it already to P2 of R for this example. So see, before I even start, I already am expecting these two numbers to add up to 2 because the dimension of R2 is just 2. It's just so nice when you know that, right? So let's just pretend that we are really good at doing kernels. We know how to calculate it. I'm kind of afraid of the range. Not so sure we know how to do the range very well. Well, you know what? If we focus on the kernel first and figure out what goes here, that'll already give me some very valuable information about the range that'll make that part of our task easier. If we know already what, one of these dimensions is, it'll tell us what the other one is. And we can use that to our advantage. Right, so let's go ahead and let's try to figure out the kernel here. Okay, so for the solution, you don't always have to start with the kernel, but I guess that's what I'm doing. So to do the kernel of T, I'm just going to take the transformation T of AB, and I'm going to set that equal to 0. Right, and then I can write down what T of AB is. This is going to be A plus the quantity B minus 2A times x squared. And so this is still being set equal to 0. Just to be completely clear, when I write 0 here, I really mean 0 plus 0x squared, right? We can literally think of it term by term. And as such, we then know that, the constant terms have to be matched up, right? They have to line up. And then the x squared terms also have to line up. And that's how I'm going to create my equations here. The first equation is just A equals 0. And then the second equation is B minus 2A is equal to 0. So both coefficients have to actually be 0. All right, and now this is easy to solve just in our head. If A is equal to 0, then so is B. So we actually conclude here that in this example, A and B, they are both 0. They're both going to be equal to 0. And so my kernel of t is just 0, 0. There's no free variables here. There's no free variables whatsoever, so we can just go ahead and put 0, 0 there. And what is the dimension of that anyway? It's just 0, right? Did somebody say that? Yeah, it's just 0. It's a trivial vector space. There's no basis. You can't really write down a linearly independent spanning set for just the 0 vector. So when we come back over to our table over here, we actually already know this is a 0. And see, if I know that ahead of time, then even before I've done anything with the range, I already know its dimension. Right? I already know that this has to be a 2 because it has to add up to 2. Agreed? Let me show you why that might be helpful for us. I'm going to show you why that's actually really interesting, that we know the dimension of something before we even calculate it. But that general rank nullity theorem is very helpful for doing that. Let's say now I want to go back and do the range at t. I already know it's going to be 2-dimensional, but what actually is it? And can we get a basis for it? Let's try it. Let's try it. So for the range of t, remember, we're going to take the span of the transformation of a basis for R2. What's a nice basis for R2? Go ahead, Bryce.
Parentheses 1, 1, 0.
1, 0.
And then 0, 1.
And then 0, 1. That's probably the nicest example of a basis that you could have. It's not the only one, but it's as good as any other, probably better computationally than any other basis. So this is all we're going to do, guys. We're just going to figure this out. Let's just see if we can calculate t of 1, 0 and t of 0, 1. So I'm putting a 1 for A and a 0 for B. If I do that right here, guys, if I put a 1 for everywhere I see the A, and I put a 0 everywhere I see a B in this formula, right? I'm looking at this formula here. This is what was given. Putting in a 1 for A and a 0 for B, I believe that's 1 minus 2x squared. Okay. And the second vector, right? If I put in a 0 for A and a 1 for B, 0 goes in for A and a 1 for B. That 1 is right here being multiplied by x squared. This just gives me x squared. Okay. So, you see, you might be nervous that these could be LD, except that we know that they aren't. Because we already know that the dimension of this range has to be 2. So if these were LD, then we would be removing something and be left with a basis that was too small for what the dimension of it is supposed to be. Now, I realize that you guys are probably looking at this saying, oh yeah, I can tell that those are Li. It is pretty easy to see that. It's only 2 vectors. They're not scalar multiples of each other. But imagine that there were 5 polynomials sitting here side by side, a big mishmash of a whole bunch of polynomials. And you were like, oh my gosh, I don't want to have to figure that out, right? But if you knew that the range was 5-dimensional because you had already calculated the kernel, right? Then you would be able to say confidently that even without doing any work at all, that those vectors would have been a basis. They would have had to have been Li because it was the right number of vectors for your basis. Isn't that amazing? This is what mathematicians love to do. They love to create functions between vector spaces that they do understand very well already into some other universe that maybe they're a little fuzzier about, right? And so I've got some vectors I'm a little fuzzier about. I look at these polynomials. I can't tell if those are Li or not. But wait a minute. I've got this beautiful theory that connects the 2 sides of my transformation, right? Something from the kernel. Something about the kernel and the range and their relative sizes. This is like a hugely sophisticated way of using math to take our good knowledge about one universe and use it to help us understand another universe. We now have a new proof today, a new proof that these vectors are Li. I don't have to throw them in a matrix. I don't have to go back to the definition of Li and work it out. I can just say, hey, I have figured out ahead of time what the dimension of this thing is supposed to be. And I know that I now have the right number of vectors to match that dimension. So that's got to be a winning set of vectors. That's got to be a basis for me. So that's really, really cool. So that's it. That's going to be it, right? My basis here. We can go ahead and officially indicate that there. That is my basis. And so that is a 2. Okay. Let's just say for a minute that you weren't as comfortable with kernels. Let's just say for a minute that you had not done the kernel part. Okay, I'm standing in front of it as best as I can. You can't see what's behind me. And I ask you to find the kernel and the range, basis for a kernel and the range. And you start with that. Now, of course, if you start over here because you're comfortable with ranges and not so much with kernels, then you would have to check that these are Li. Because you wouldn't be able to, you wouldn't know yet that this was a 0. But see, let's suppose you started with the range and you figured out, okay, the range is 2-dimensional by just doing this part of the board work first. Then, okay, you're not so confident with kernels. I have good news for you, because if you figure out that this is a 2 first, then from this equation again, you'll be able to say that this one is 0, right? Immediately. And of course, then that means you don't have to do any of this work. Guys, you almost never have to do all of the work for the kernel and all of the work for the range. You never have to do that, because this equation says, hey, if you figure out what's going on with the range, it's going to help you figure out the kernel. Or if you figure out what's going on with the kernel, that'll help you figure out the range. So you really can milk that equation nicely and draw some fast conclusions. It's just, I get really excited about it because it's a nice thing that we can really use math for, is to connect and build relationships between vector spaces. That's what this whole chapter is about, right? That's what this whole entire conversation is about. Okay, before we take a break, I would like to give you a couple of definitions that are associated with this kernel and range conversation, and just try them out on the, we've got 6 examples on the board or in front of us now, and I think it would be a good time to do this. Technically speaking, I'm actually kind of moving into the next section of the book to make these definitions. So we're kind of jumping up to 6.4. So far today, everything has kind of been 6.3. But let's make a definition here. The first part of this definition is just, if the kernel of T is just equal to only the 0 vector of V. So if the kernel of T is a trivial vector space, then we say T is 1-to-1. A 1-to-1 transformation. Sometimes I'll write that as a 1-1. 1-to-1, a 1-to-1 linear transformation. It just means the kernel is 0. Okay, if the kernel is just 0. So that's one possibility. And then the corresponding definition that usually everybody talks about these two things together. The second one is about the range. If the range of T is actually the whole entire W. So I'm going to remind you that that blue circle in the W side of my original diagram today, that blue circle might not be the full huge W, but if it is, again, what does this mean? This would mean that everything in W is realized as an output of the transformation. There is some arrow that goes into everything. The range of T is huge. It could be, if in this case, we say T is onto. T is onto, right? So the transformation is onto if the range of T is equal to W. And then finally, there is a third thing that puts the two together, which is that if T is both 1-to-1 and onto, if it is both, so if the kernel is 0 and the range of T is equal to W, then then we call T an isomorphism. It's a big word. Algebraists love
boy.
this word. It's used in a lot of places, not just in vector space theory. It's used in many places in isomorphisms. So this is just a transformation that is both one-to-one and onto. And we will, in that case, I will add a little bit more here. And we say, in this case, we say that V and W are isomorphic. V and W are isomorphic in that case, right? So it just means if there is an isomorphism between them. When two vector spaces are isomorphic, it means that from an algebra point of view, from the point of view I would care about, those vector spaces are basically the same. The algebra works exactly the same. So if I have one vector space where I'm doing things like red plus orange equals blue, and green plus green equals purple, and purple plus white equals red, and blah, 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 right? I could take that vector space of colors that you guys all saw in my exam on Tuesday, and I could change from those colors to the vectors are cell phone, water bottle, glasses, cap, notebook, and whatever, iPad, right? And I could make a whole new chart where we have water plus glasses equals iPad, and iPad plus cap equals cap, or whatever. And it would just simply be the same vector space, essentially. The actual vectors are different now, right? Instead of 6 colors of the rainbow, instead now it would be 6 different objects in this room. And we would have a addition placed on that collection of objects. But structurally speaking, as an algebraist, which I am, I would say that they are basically the same. They are isomorphic vector spaces. In fact, there's a notation for this, which is we don't quite use an equal sign because we don't want to literally say that these vectors are the same. Obviously, a color of the rainbow is not the same thing literally as an object in this room. But the way the math works in that exam problem would be considered by somebody like me, who is an algebraist. The way that math works would be the same as the way that the math works, assuming I have a correspondence in the table. It'd be the same as the way that the math works on the 6 objects in this room, right? And we would say that for all practical purposes, those 2 vector spaces are the same, right? So when 2 vector spaces are isomorphic, that is a powerful statement that structurally speaking, it's as if they're the same. They're not literally the same, but for all intents and purposes, they are. Okay, guys, before we take just a short break here, I just want to go back to these 6 examples right now, and I want to figure out which ones are one-to-one and which ones are onto, and both or neither. Oh, that sounds like a question. Given a transformation T from V to W, is it one-to-one? Is it onto? Is it both? Or is it neither? That's absolutely the kind of question I'm going to be asking. It sounds like the one that we did earlier for, what was it? Linear independent, spanning set, both or neither. And we're going to see a lot of parallels there. Okay, so let's just go back here though, before we take a little break. Are any of these transformations one-to-one? We got the 6 examples here that we've looked at already today. Are any of those one-to-one? Let's see, one-to-one, that meant that the kernel needs to be 0. Jordy?
6.
The very last one. Yep, absolutely. 6 is a kernel of 0, dimension of 0. So this one right here, number 6, is one-to-one. I mean, we still have the work on the board, right? The kernel of T was just 0. So that one is one-to-one, number 6. Let me put that one-to-one right next to 6 so I don't confuse anybody about that. That one is one-to-one. Number 4 might be one-to-one if the nullity of the matrix is 0, which is possible. If there's no free variables in the row echelon form of A, then that would be an example of a one-to-one transformation as well. Okay, so that's the only one that's, so maybe I could just I'll put a question mark on this one. Because it does depend on what the rank or the nullity of it depends on the matrix, basically. So I can't give a specific answer there. What about the onto? Let's see, so the onto, the range of T is supposed to equal W, so this is gonna be measured just by looking at dimensions again. Right, so if I look at what is the dimension of the range as compared with the dimension of W. Let's look at all of these 6 examples. The W's are in this column right here. These are the W's. Does anybody see any of these where the size of the W is actually just the same as the entire range of the transformation? Taylor? Okay, if we look at number 3, look at your W, it's P2 of R. Then what was the dimension of the range? It was 3. That's exactly the same as the dimension of P2 of R. So that means that in that case, the range of T is the whole codomain W. It's the whole output space W. So number 3 is onto. Anything else? Bryce?
5 possible?
Yeah, if we look at number 5, this one's a little bit of a trivial case. When I look at R, just R itself is only one dimension. It's like R1, which is just one dimensional. And I've got a range that's one dimensional there. So that matches up as well. So this one is also onto. Exactly. Okay. The first 2 that we did up here at the top, neither one of those is 1-to-1. And also the ranges are too small. Because notice that W in the first 2 examples was 4-dimensional. And these are just 1s and 2s, not big enough. So these are neither. This one is neither. And this one is also neither. And so you've got a really good foundation for a new type of question to play with. I give you a transformation and I ask you, is it 1-to-1? Is it onto? Is it both? Or is it neither? And you may remember that when we did the corresponding question, do you remember when we did, like, I would give you a set of vectors and we said, are they Li? Do they span V? Are they both or are they neither? Do you remember that you could always like cross off 2 of the wrong answers right away by just comparing the number of vectors, the K value, to the dimension of the vector space? Right? You could always do that because there was kind of this rubric that we learned. Well, it turns out there is also a rubric for this. There is also a rubric for this. We can, at a glance, cross off 2 of the 4 wrong answers in just a matter of a second. So I'm going to make you wait 10 minutes or something to hear I'll give you the full story on that. But let's take a moment to decompress before we do that. It gives you guys some fresh air and take a little break. Yeah.
Okay. And are you ready? Yeah.
I use some fingers and also for the whole class.
You want to pass those out?
Yeah.
I think our SI here has decided a nice Halloween for us. So thank you for doing that.
Thanks, Janda. You're my hero. Are you gonna do it in SI session too?
Yeah.
Oh, double the.
Oh,
stats.
okay. Oh, hey, Janda. I am. Thank you.
Nah, dude, I don't get out of work till 10.
You can drink your Coke if you like.
Thank you. Yeah, I'm sure I will here very soon.
Yeah.
I gotta get on that grind, dude. I gotta make the money. Gotta make the money.
Yeah, Janda, I stole all the candy from the Legion.
Oh.
I'm joking. I just asked for all of it.
Oh, down.
You want to kick that?
I'm down. Thank you. Thank you. Thank you.
Welcome.
Oh, man. Oh, thanks.
Where'd you get these again?
Well, there was a guy who was giving candy out.
Oh, shit.
It's a trick or treat.
Oh, he gave it to you?
Yeah. I got a bunch.
He hooked it up. McDonald, what are
What's this?
Not from Taiwan.
What?
What?
What are they?
Right.
You got it from Taiwan?
Yeah.
Oh shit. Good luck.
Yeah.
I needed that
Take
like,
it before a test.
I needed that Tuesday.
Tuesday? Oh, you have a test on Tuesday? Oh, yeah. Well, maybe you should take it now, so later on, yeah, good luck.
How long does it last? I haven't pressed on Monday and Tuesday.
How long does it last?
Does it last till then or sorry, wait. Come on, you're the one setting the bar. What's the what's the real one?
Last one.
24 hours? Okay, so I'll take it Monday night. Monday night. Alright. I'm down with it. I'm down with it.
Right. Oh, for sure, for sure. He doesn't tell us. Perfect. No, it's.
It's like biscuit. Have you ever had shamrock shakes at McDonald's?
Do full cost.
Yeah, it's
Like I just.
Never tried it.
I don't know. I've heard it. Like I think I'm. Obvious one. I don't want it. Doesn't matter. It's fine.
You have McDonald's shake before?
And a Kit Kat free.
I share all this stuff. This is wonderful. I don't know if you remember last week, I kind of got a little sick at the beginning of class. I think I'm gonna save it for afterwards.
Yeah.
So I don't get too much,
And that candy I gave you.
yeah. Oh, is it really?
That gives you go along.
Oh, I need all the luck I can take. Yeah, thank you so much.
They should trick or treating.
What's that?
Dig after you're feeling better.
Yeah. I mean, I'm feeling fine now. I just don't, I've learned my lesson a little bit. Yeah, not to like put too much inside of me when I'm doing this class. Yeah.
Professor, since you love Halloween, I deserve to go trick or treating tonight.
Are you gonna go?
Well, if my mom. All right.
What was your go-to costume? Annan. Professor Annan? Huh? A cow. It's different as a cow. I have a cow onesie that I always put on. Cause I was like a dairy cow, so I always wear that. First time. A dairy cow, yeah. It's 2 years in a row. 2 years in a row. You gotta do it. It's a cow, man. But I gotta lay on. I gotta work tonight. That's the time, man. Heck no, bro.
Then just dress up before you go to work.
Oh, I'm good with that. I'm good with that. I have mental pictures. That's all I need. That's all I need. Mental pictures. Oh, yeah, I saw Spider-Man out on the ground. Yes, Elvis. I haven't seen Elvis. I was gonna try to do an Elvis impression, but nah, I cannot do that shit right now. Before I embarrass myself. No, no, no. I could have my shit on, so it makes it even harder to talk. I'm good. I'm good. I can eat, but just without my teeth. I just gotta take it out. It looks so funny when I take it out, dude. Fucking go. Huh? This? I like this a lot more. My type of thing. But yeah, you texted and I saw.
Hey, next year try going to Disneyland.
Yeah, no, I don't know how the fuck he did it. And he showed like trial.
Disneyland has all this stuff.
Only showed like, I woke up too late.
Yeah.
I got to get up early. Yeah, I wanted to see the midterm. He was like, oh, you gotta wait till then.
Like always.
Scared, I'm scared. I don't know, bro. I'm fucking worried about it. I didn't think of it, like, think about it.
I just-
Is
there even white? Jackson.
Yeah. Yeah, I know. Like if it's like fresh and everything, but once I forgot like the question, I'm like, alright, it's too late, man. It's too late. No, Diego, he'll talk about it like weeks. after. I'm like, fuck, man, I don't even remember what was like question 2. I know, no, they will be like, oh, you remember, I finally figured out question 4. I was like, bro, that was like 3 weeks ago, dude. I don't even remember what the fucking values are. Yeah. but
Once I quit playing, going straight to that.
Are you?
Oh, the roulette. Yeah. It's when you. Yes, I know there's not that impossible. You have to do a lot of your song. Oh, really? You have a good briefcase like that too. Like how I just gotta get that good card.
Yeah, every year they move their, let's use it, so they get.
Yeah. No, but no, there's there's the chips themselves, are just tokens to play. And the token, the tokens you pass them around, basically if you have a token, I'm sure you know that. See, I really like one of the. One place. The bar. Exactly, it's twice as much money. 99% of gamblers quit. Exactly.
Try to get us back together here again for a minute. This is good stuff. I think we're making some progress here on understanding the kernel and range of a linear. I sort of foreshadowed that we'd be having these questions about whether T is 1-to-1, 1-to both, or neither. Very popular questions for me to ask. And so I've got 2 practice problems that I wrote up for us to look at during the break, and I'd like to do that right now. Oh, you know what? I did not quite write the first one totally out. This one should say the dimension of the kernel is equal to 2. I needed to say that. So anyhow, let's take a look at these 2 questions and see if we can answer whether the transformation is 1-to-1, onto, both, or neither. I didn't actually write out what the formula is for T on this first one, did I? I just said T is going from P6 of R to R5, and the kernel is 2-dimensional. So let's just take these one thing at a time right now. So I don't start doing the solution. I didn't leave myself much room for the solution, and the reason for that is it doesn't take much writing to get the solution here. It's actually very, very easy to get the answer. So for example, can you guys tell me right off the top of your head whether this is going to be 1-to-1 or not? I mean, what does, I've kept the definitions up here, so if you need to look over, by the way, this is all really good stuff for flashcards. You need to learn all these definitions. So 1-to-1 is just that the kernel is 0. So would this be 1-to-1? No,
No.
we were given that the dimension of the kernel is 2, so this is not 1-to-1. Since the kernel of T is not the 0 vector. Okay, so that's the first part. And now let's talk about the onto part of it. Can we decide if this is onto? Let's see, onto means that the range should be the same as W. Let's take a look. Here's W, right?
Yeah.
W is 5-dimensional. So can we figure out what the dimension of the range is? Is that possible? Well, I kept this on the board too, right? So, yeah, Angela, do you want to help me with that?
Yeah, we can use the theorem.
Absolutely, yeah.
The current is equal to 2. If the IV is.
Exactly. The dimension of P6 of R, we know that that would be 7. That's my vector space V. And so that has to be the sum of these 2 numbers. And so this is just going to be 5, right? So the dimension of the range is 5, and that matches what W is. So that means that W is equal to the range of T. So here, let's just add that here. The dimension of the range of T is equal to 7 minus 2, which is 5. And that implies that the range of T is equal to R5. It's 5-dimensional. It's a 5-dimensional subspace of R5. So it equals R5. And so T is onto. So T is onto, but it's not 1-to-1 in this example. This one would be onto, but not 1-to-1. Are any questions about that? This is even before, I didn't even have to get into the nitty-gritty of what the formula for T was. I just had to know what was V, what was W, and can I figure out the dimensions of the kernel and the range. It's just that fast. Pretty nice. Okay, let's take a look at the second one here as well. This time I decided to just practice on a matrix transformation for a minute. So this is a transformation that goes from R2 to R2. And in that context, we would expect to find a matrix A that would have a size of 2 by 2. Okay, so we have it, I actually wrote down the matrix here. A is this 2 by 2 matrix right here. Okay, and I would like to again decide whether T is 1-to-1 onto both or neither. So I have to think about the kernel and the range of this kind of transformation. And so we still have that over here. If I look at item number 4 on my list, when I have a transformation from Rn to Rm, I know what the dimensions of the kernel and the range are. They are simply lined up with the nullity and the rank. So if we just take this matrix and figure out what its rank is and what its nullity is, I bet we'll be able to answer the question. Right? So I can do an ERO here really quickly. I'm not going to dwell on it, but I can zero out that second row because it's a multiple of the first row. And so what is the rank of this matrix then?
1.
Only 1, right? So the rank of A is 1. And what would be the nullity of this matrix?
1.
Yeah, see, that's also 1. The nullity is the number of free variables. They're both equal to 1. In other words, what we have is 1 plus 1 equals 2. Right? 1 plus 1 equals 2 in my formula. But the rank is the dimension of the range of T in this case. And the nullity is the dimension of the kernel of T. Just from the columns over there. So is the kernel equal to 0?
No.
Not a chance. It's actually one-dimensional. The kernel is not 0. Is the range equal to the whole entire W of R2? It's only one-dimensional, right? That's not big enough to be the entire R2, which is 2-dimensional. So this thing is neither. This is not onto or 1-to-1. The kernel is too big and the range is too small. Basically what it comes down to. So this one is for the solution here. I'm going to write it just, sorry guys, just right here briefly on the bottom of this board. I'm just going to say neither. And if I want to explain that, all I have to do is look over here at these values. The range is not equal to R2. The kernel is not equal to 0. So this one is neither. Marcus.
Wait, so why does I guess information about A lead to what we can say about the transformation itself?
How does information about A lead to information about the transformation itself? So if you remember from the handout, when you calculate the kernel of one of these kind of transformations, you get the null space of it. And when you calculate the range of one of these kind of transformations, it's the column space of A. So that was how the actual spaces came about, and then their dimensions are just the nullity and the rank respectively.
Right.
Yeah, just from number 3, I guess, on the handout. Yeah. Actually, we can make a more general statement that I think I'd like to add to the notes here. So this is a general note that would be worth writing down about this kind of a situation. So if I have, if I am given a transformation T from Rn to Rn via T of x equals A times x, then T will be an isomorphism. Remember that just means it would be both 1-to-1 and onto. T would be an isomorphism if and only if something was true. And I'm wondering if anybody knows what I'm going to say right down here. Do you have an idea, Maxwell? We could say it that way. That will be a side comment as well that we could make. But what could you tell me about the matrix A itself? I mean, I'm looking for one very, very important word about a matrix that we have been using for many weeks. Yes.
Invertible?
Invertible. Yes, it has to be invertible. Again, why is that? Well, if T is an isomorphism, it means that the kernel is 0. That means the nullity is 0. And the rank is n, right? This would be n plus 0 equals n. And if we remember our invertible matrix theorem, remember that for an invertible matrix, the rank is n and the nullity is 0. And the determinism is not 0. So we could also say that, but yes, this is how I would like to have this statement written. A is invertible. We literally, if we wanted to, could add this as yet another bullet point in my big long list for the invertible matrix theorem. So this kind of transformation, a matrix transformation, will be invertible and will be an isomorphism if and only if A is invertible. Well, you can see right here, this matrix, very much not invertible. If you take the determinant here, 1 times 4 minus 2 times 2, you get 0. This matrix is not invertible. So of course, we do not have an isomorphism. And in fact, this turned out to be neither. This was actually no on both accounts. All right, so that's consistent with that as well. Okay, so gosh, really important results today about these linear transformations. I'm gonna try to address this 4-part multiple choice question with one more set of facts for you that will, as I mentioned earlier, it's going to remind you of the 4-part multiple choice question that we had in chapter 4 about basis and linear independence of spanning sets. So I don't think this is going to come as too big of a surprise. So there's going to be 3 of them here. They're all very easy to write down. And they allow you to cross off 2 of the 4 wrong answers immediately from this question without even taking a breath. So the first fact is that if the dimension of V is bigger than the dimension of W. Okay, so you're going to want to write these down, and this is also, I would say, note card worthy. This is worth starting to memorize because there's 3 of these and they can get jumbled up if you're not careful. If V is bigger than W, guys, then T cannot be 1-to-1. It cannot be 1-to-1, and I'll say it might be onto. Okay, so I need to erase a little bit more first, so I have enough room to write all of this. There is no way that a transformation could be 1-to-1 if V is bigger than W. It's actually very easy for me to explain that to you. Because we have our rank nullity theorem, the general rank nullity theorem, which told us that the dimension of V is the dimension of the kernel of T plus the dimension of the range of T. Dimension. You don't need to take notes on this. I'm not going to be quizzing you on this. I just want you to understand this point. Guys, if V is already bigger than W, and the range of T is inside of W, then that means that V has to be bigger than the range of T. Just think about size-wise, right? V is the biggest thing you have. V is bigger than W, and then even smaller than W would be the range of T inside of W as a subspace. So V is bigger than the range of T. So there is no way that this number could be 0. If this number was 0, you would be saying that V was the same dimension as the range of T. And that's not going to happen. If V is bigger than W, I promise you, the range of T has to be smaller than V. And so this has to be a positive value, which means T is not 1-to-1. Remember, 1-to-1 means that the kernel is 0. So these facts can all be explained just from this formula. So it's not that bad. The second fact, of course, is just the reverse scenario. If the dimension of V is less than the dimension of W, then T cannot be onto. It cannot be onto, but in this case, it might be 1-to-1. Okay, so that's just the reverse situation from the first bullet point. And then the third one as you, I'm sure know it's coming, is what if V and W are the same size? If V and W have the same dimension, then what do you suppose I'm gonna say? Both or neither, both or neither. It's just like the cases we had in that earlier scenario. T is both or neither. That is exactly right. T is both or neither. And of course, the both case, just to remind you again, that means isomorphism. So T would be an isomorphism if it was both. And the other option is neither. And we've actually kind of spelled out that at least in the case of a matrix transformation, I know exactly when it will be both and when it will be neither. It will be both if A is invertible. And so if A is not invertible, like on this example that we just did, then it had to have been neither, right? Has to be neither in that case. So that's it. That's a nice sort of three-part list of facts. All of them are pretty much explainable from this general rank nullity theorem. We don't really have to work any harder than that. Questions at all? Pretty easy. Okay. One last thing here, and then we're gonna call it a day pretty much. I just want to point out that you will get asked in the homework, and you will want to know how to do this anyway. Sometimes they will ask you to actually construct an isomorphism. In other words, so far this whole chapter, you've been handed what T is, and you've been asked to do stuff with it. Show that it's linear. Find the kernel, find the range, these kind of questions, right? But sometimes we can be in a position where we want to create this isomorphism or this transformation ourselves. So I'm just going to give you a quick example of that. This will kind of get you off and running on the homework as well. Let's suppose I ask you to construct an isomorphism T going from, let's say, from M2 of R to P3 of R. Let's say I ask you to construct this. First of all, just for a quick sanity check, in order to have an isomorphism, in order for it to be both, V and W have to be the same size. If V is bigger than W, you're not going to have an isomorphism. If V is smaller than W, you're not going to have an isomorphism. They have to be the same size, so just check the dimensions, right? They both have to be, in this case, they're both 4-dimensional. They're both 4-dimensional. So this is at least reasonable. But we can't just write down anything, because half the time, basically, your T could end up being neither if you're not careful, right? So we have to just be a little careful. So I'm just going to give you, there's many right answers here. I'm going to give you, I'm going to have you guys help me come up with an easy one. I'm going to plug in, this is the solution. I'm going to plug in a 2x2 matrix, and what I have to do is spit out a cubic polynomial, right? P3 of R, that's polynomials of degree 3 or less. Does anybody have a suggestion for me about how I can take 4 numbers, A, B, C, and D, and create a cubic polynomial out of them? Liam?
AX, B, X squared, C, X.
It's exactly right. It seems almost too easy to be true, but that's exactly a natural way to do it, right? Turns out this is a beautiful example. If you check the kernel of this, it will be 0. If you check the range of this, it will be the full R, the P3 of R. So it is 1-to-1 and onto. This is an isomorphism. And I was talking earlier about how people were there were some problems on the midterm, right? Which is what I'm going to talk about next. Anyway, there were some problems on the midterm that involved polynomials. And I saw people drawing slots on their exam. By the way, you could also create an isomorphism to R4. I could have added R4 down here as well. That's also 4-dimensional, and that would be yet a third example of a vector space that's isomorphic to the other two. So I saw people on the midterm taking polynomials and then writing down slots. And, you know, so they would have something like this, but it would look like this on the paper. And of course, I had to say something about that because technically this is not a polynomial, right? And things sometimes need to be expressed as polynomials. But I can now give you a little bit of redemption about that, because what you might have been sort of doing without realizing it is using this isomorphism that exists between these different worlds. I have 3 different worlds on the board here, R4, M2 of R, and P3 of R, and they are all basically the same, right? These are isomorphic vector spaces. You know, if I went home tonight and I did a big, massive calculation using 2x2 matrices, right? I don't know whatever it is. I want to go calculate something, blah, 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 blah. I have a whole page. So I fill out a whole page of stuff about matrices and I bring it into you guys, right? So Dr. Hannon has this page of scratch work of calculations with 2x2 matrices. And I bring it into you guys and I ask you, rewrite the whole thing using polynomials instead. You could do it. You could do it because you have this dictionary that is created by T that takes a matrix and associates it to a polynomial. It's actually a two-way street here. So you could, so if I did this part right here, right, then the class could take my notes and then basically rewrite it using polynomials, right? And you'd have total comprehension of what I had written down in the world of, sort of in the notation of matrices. You're writing it in the notation of polynomials. And other than the way we're writing the notation, math and the algebra is totally compatible. We would completely be able to understand each other. That's pretty neat. So if you don't like polynomials, you never want to see a polynomial again in your life, just figure out how to make an isomorphism from it to some other vector space that doesn't have polynomials. And that'll be good. So that'll be good. Okay, I'm going to stop there. I have about